Welcome back. We're going to be looking at Lesson 3, Histograms and Numerical Measures. So here we have a box plot. And from this box plot, we want to know what is the shape of the underlying distribution. And in this case, we just don't know. Seems like there's a slight right skew, but underneath, this describes the weight of the football players. The shape of the distribution of the weight is bimodal, and the box plot does not show the bimodal nature of that. So there's a gap inside this distribution, and this gap is not evident through the box plot. So the box plot just shows us a density. So it shows us that 25% of all data points kind of lie in this general range, 25% lie in this range, 25 in this range, and the last 25% lie in this range. So the quartile spacing is a density reading. So we've got the minimum, Q1, median, Q3, and the maximum. And depending on the length of each of those segments, that represents a roughly same number of data points. In this case, it's players. So 24 players are between the minimum and Q1, 25 between Q1 and median, 25 between median and Q3, and 24 between Q3 and the max. Now what a histogram does is it gives us a picture of a frequency table. So if we were to look at each of these bins, so 170 to 189, in this case, each of these in this picture is 20 apart. So if we were to go into our studio, I'm going to go ahead and import the Pittsburgh Steelers football roster again. So I will call it, it's always good whenever you're importing data to rename it to something that's pretty easy to type. So in this case, Steel for Steelers. And I'm going to make a histogram. So hist is my function. And as we do with R, I'll say which data set am I looking for? Steel, and then what variable? Weight. So this makes a histogram of the weight. And you can see each of them looks like is 20 or so apart. Now I can edit this picture. So main is Pittsburgh Steelers 2026. And that's going to change the title up there. I can hit up, and that brings up the last thing I did. So comma, shift, enter takes me to the next line. xlab labels the x-axis, and in quotation marks, I'll say weight in pounds. And now we have a good looking histogram. So making a histogram in R, that's the general structure. We've got the data set, and we've got the variable of interest. We can also, like I said, change the main title and change the label. Now, with histograms, you might not like the initial shape bin distribution. R picks something for you by default, but if you want to vary that, we're going to use a function called breaks. So back to our R studio, I'm going to do up to the left, comma, and I'll do breaks is 5. So the breaks 5 command will do approximately 5 bins. Let me see. Oh, it should be breaks. All right, so it doesn't give you exactly this many. It still kind of uses its own judgment. So in this case, it gave me 4 bins. So that is not a good picture of the shape of the distribution of weights. So I'm going to try breaks is equal to 10. That looks pretty much what we had. So that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, that's exactly 10. If I was to do breaks is equal to, for example, 12, that now gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Looks like 18 different bins. So you can see there's a little bit of like trial and error with that. I'm going to do breaks is equal to 20. See what that looks like. That's no different than 12. Now I'm going to do breaks is equal to 40. That should give me something that's categorically different. There you go. So from all those, depending on what you want to show, you might want to play around with bins to find something that matches what we want. So I think that breaks is equal to 10 probably had the best general picture that shows the bimodal nature of the distribution of weights. So a histogram is not a bar chart. So a histogram shows quantitative data. So this is 200 pounds, this is 250, so 240, etc. And different players kind of fall in each of these categories, and it is continuous, so that someone who weighs 300 pounds weighs 100 pounds more than somebody who's 200 pounds. Like there's a natural progression there. A bar chart looks at categorical variables. So for example, hybrid players, linemen, skilled players, or it could be freshmen, sophomores, juniors, seniors, or for example, someone living off campus or on campus. And there's not a natural order. So like off campus, on campus, it doesn't matter if one of the bars is on the left and the other one's on the right, or vice versa. But on the x-axis, if I'm doing a histogram, right, I can't have 300 to the left of 200. Like it has to be sequential. So let's look at the 3 different displays we've looked at, the stem plot, the box plot, and the histogram. So the stem plot and the histogram both have a pretty clear shape. The box plot, neither the box plot nor the histogram shows every single value that is in our distribution, whereas the stem plot does. Stem plots are not good past a lot of values, and we can take a look at that here in a second. And box plots clearly show the presence or absence of outliers. Histograms often don't. Stem plots, they don't do it explicitly. So the box plot is the only one that cannot show shape, but it's one that compares groups very well. So why we stop using stem plots? If I have 560 students from Virginia Tech and I want to look at their grade point average, the general stem plot is going to be a mess. So I just imported a database of a random sample of 600 Virginia Tech students. So if I do n row VT, you can see there's 600 different students. And up here, you can see the different categories: student ID, year, college, gender, in-state, residence, GPA. So if I do a histogram of VT students' GPA, it's a strong left-skewed distribution, and that represents 600 students. If I do a box plot of that, so box plot VT GPA, gives me that. Let's turn that horizontally. Looks like that. Good evidence of a left skewed distribution and pretty good representation of the data. If I do a stem plot, it's a pretty big mess. So it's hard to, you can kind of see the shape, but also it's difficult to kind of figure out what the GPA is of these people, and with 600 different students. Yeah, it's like I said, it's just a mess. So a histogram is a much better representation of a large data set of continuous data. So sometimes the box plot does give you the correct shape. So sometimes it doesn't, as we saw with the bimodal distribution. But when you have a shape that kind of is more compact to the right of the median, and then when you go to the left of the median, it's starting to stretch out, and you've got a cluster of outliers, very likely it's going to be a left skewed distribution. And kind of conversely, if I flip it and you kind of have the same shape, right, something that looks sort of like this with a bunch of outliers on the right side, very likely it's going to be evidence for a right skewed distribution. So numbers that go with the picture, mean and median are good values for the center of a distribution. Looks like there's a typo here. For spread, range, maximum minus minimum, IQR is Q3 minus Q1, and standard deviation. Standard deviation is basically the average distance from the center. So standard average distance from the center, we like from the mean. To find the standard deviation, we would find the mean, and there's a formula that basically says, on average, how far is each individual data point from the center, and the bigger the standard deviation, the farther on average the data points are. You don't have to know the formula, you just have to know the general idea of what standard deviation does. All right, so imagine there are 12 people in a room, and one of them was a 24-year-old student, and that student leaves, and a 60-year-old student replaces the 24-year-old student. So here is the data in order. The 12th person was a 24-year-old, and now they are replaced by a 60-year-old. So this is the distribution of student ages beforehand. This is the distribution of student ages afterwards in the room. And I want to look at what effect did replacing a 24-year-old with a 60-year-old have. So the mean got bigger. The standard deviation got quite a bit bigger, and the range, max minus min, also got bigger. The median was unaffected, right? If I replace the oldest student with one who is much older, my median, which is the average of the middle two, stays the same. And my interquartile range, the difference between Q1 and Q3 does not change. So because of that, we call the median and the interquartile range resistant. Resistant means that they are unaffected by extreme outliers, and not resistant are ones that are affected by extreme outliers. So a couple things to remember. Histogram shows shape, a box plot often cannot. Sometimes it might give you clues to the shape, but it doesn't explicitly show it. Quartile spacing tells you what percent of the data is between 2 points. So 25% of the data is between the minimum and Q1, 25% between Q1 and the median, et cetera, et cetera. And both the mean and the standard deviation are not resistant, whereas the median and IQR are resistant.